All right. Good morning, David, Francis, Ezekiel, Leon, Grace, and Michael. So, welcome to a brand new week for Math 174. I hope exercise 5.1 worked well for you yesterday. So, for today, we'll start discussing Module 9. By the way, Module 9 is third to the last among our modules for the course. So, kakaunti na talaga. We're near the end of the course. Well, Module 9 is about another another quadrature rule aside from the Newton cotes formula that we discussed last time. Module 10 will be about Romberg integration, which is an accelerator method for quadrature formulas and also improper integrals. And then module 11 would be Monte Carlo simulation, which is another way of approximating integrals, but without using quadrature rules. And that method is highly probabilistic compared to the deterministic nature of the quadrature rules that we have seen so far. So with that, here is just some things about Module 9. So we'll cover it for this particular week. And then the lab session for the contents of Module 9 would be November 29th. So that's going to be on Monday. And the lab exercise that is at the end of Module 9, which is actually the second part of exercise 5, will be due also on Monday right before midnight. Okay. And we just have two objectives for this module. Number one is to derive probably one or two Gaussian quadrature rules. And of course, before we derive them, we'll discuss what they are. And second is to use these quadrature rules to solve scientific problems. And then I have several other references here. I will cite some results from this book by Abramovich, which is a very nice reference, especially if you're working into numerical analysis or even mathematical physics. Actually, ito yung ginagamit ko dun yan yung ginamit ko sa PhD dissertation ko. And apparently, meron siyang result about numerical integration na pwede nating i-cite today. Hindi natin ipoprove, isa-cite lang natin siya. Pero amazingly, nung nire-review ko na tong book na to for my dissertation, saka ko lang na-realize, oh, meron palang formula para dun sa weights ng Gaussian quadrature rules. So makikita natin yan later. This, I think, is the first time that I incorporated it in my Math 174 work text. So dinagdag ko lang siya before the semester started. And there's a good Wikipedia page for Gaussian quadrature rules, so you can check it out. Di ko alam, meron pa rin bang stigma dito sa atin na parang napaka-unscholarly kapag gumamit ka ng Wikipedia? Well, I actually learned that it is not that too unscholarly kasi if you are able to because maganda yung collection ng Wikipedia. They do have tons of volumes of information, and you can see articles there that are legit. Kailangan mo lang talagang i-fact check, or kung may idea ka naman kung ano yung ibig sabihin, it's a nice reference para dun sa mga bagay na alam mo na pero hindi mo natanda yung mga specific details. So I think Wikipedia is still it's a good reference, at least for reviewing things and for remembering things that were lost from your immediate memory. Pero pag gagawa ka ng scientific articles, medyo frowned upon pa rin yung paggamit ng Wikipedia. But for classes, quick researches, and quick recall, I think Wikipedia is still a good reference. Of course, with a caveat that you do your own due diligence and fact check the information therein. Okay. But with that, let's go. Let's start. Let's discuss Gaussian quadrature rules. Last time we characterized what quadrature rules are. We said that a quadrature formula for an integral, okay, is actually form is a linear combination of the function values, right? So it takes the form function value at certain abscisses times some weights associated with each of the abscisses. You take the sum from 1 to n, where n is the number of points. And if you do that, you'll get an approximate for your definite integral. And we say this is a quadrature formula that uses n points or n plus 1 points. Sa atin pala nag-start yung index sa 0 until n. Okay? Now, ito yung general classic quadrature rule. We have seen an example of a quadrature rule last time. We look at the Newton-Cotes quadrature formulas. Okay. Sa Newton-Cotes, ang itsura ng quadrature formula that will approximate the integral of f over the interval AB is you have your, of course, your function value still evaluated at the given abscissas times the weights, but the weights now take a particular form. It is the integral over the given interval of the Lagrange basis polynomial. Okay. So quadrature formula pa rin siya, yun nga lang yung weights ay determined by the integral of the Lagrange basis polynomials. So now we will look at another class of quadrature formulas. This time we will use a different set of weights. And actually this is quite different kasi this will rely on you having access to function values at specific abscissas. Hindi katulad sa Newton-Cotes na kahit anong exabytes yung piliin mo, equally spaced, hindi equally spaced, randomly distributed over the interval, pwede siyang gamitin. Kasi tingnan niyo yung formula, exaby, tapos integral ng L sabay of x. So pwede ka talagang pumili ng kahit anong exabytes over the integration interval. Okay? Pero sa quadrature rules na kikilalanin natin today, specific yung mga exabytes at saka yung mga weights na gagamitin natin. And we're talking about Gaussian quadrature rules. So if the Newton-Cotes quadrature rules use arbitrary abscissas, now in the Gaussian quadrature rules, we will be picking the abscissas so that we can maximize the degree of precision of the quadrature rule. Okay? So pipili natin carefully ano yung mga exabytes para ma-attain nung integration formula yung pinakamataas na posibleng degree of precision. Okay? And of course, once we have chosen the exabytes, we must also define, or we must also decide what are the weights associated with these abscissas. But key to this characterization of the Gaussian quadrature rules ay yung term na degree of precision. Okay? Kasi gusto nating i-maximize yung degree of precision ng quadrature rules by picking the appropriate abscissas and weights associated sa kanila. Okay? So rightfully so, we'll start with the definition of the degree of precision. Okay, the degree of precision of a quadrature rule ay sabihin, so pakidelete yung of p. So ang degree of precision ng isang quadrature rule ay yung pinakamaliit na integer m such that the integral of p of x dx from a to b is not equal to the quadrature approximate for some polynomial p of degree m plus 1. Diba remember yung quadrature rule, sila yung pinang-approximate natin dun sa integral. Yung degree of precision ng isang integration quadrature rule ay yung degree ng pinakamalaking degree nga ba? Hindi. Siya yung pinakamalaking integer na, number 1, kaya niyang i-integrate exactly lahat ng polynomials with degree less than or equal to m, pero sasablay na siya dun sa isang polynomial of degree m plus 1. Okay? So again, yung degree of precision, hanapin nyo yung pinakamalaking, or yung, actually, pinakamalaki, pinakamaliit, dahil pala binago ko na yung definition 9.1 before. Pero isipin yung ganito, yung degree of precision, siya yung pinakamalaking integer m. Mas gusto ko kasi yung alternative definition. Etong nasa alternatively sa baba. Siya yung pinakamalaking integer kung saan yung quadrature rule kaya niyang i-evaluate yung integral ng lahat ng polynomials of degree less than or equal to m, okay? Pero sasablay na siya sa pag-integrate ng isang polynomial of degree m plus 1. Okay? Kaya sabi dito sa actual definition, pinakamaliit na integer m na sasablay na siya sa pag-approximate ng integral ng polynomial p of degree m plus 1. So, kapag siya degree of precision, halimbawa 3, kaya niyang i-integrate exactly, o yung ibibigay ng quadrature formula ay yung eksaktong integral ng constant polynomials, polynomials of degree 1, polynomials of degree 2, polynomials of degree 3, pero sasablay na siya sa isang polynomial of degree 4. Okay? So yun yung ibig sabihin ng pagiging pagkakaroon ng degree of precision 3. Okay? Kaya niyang i-integrate exactly lahat ng integrals, lahat ng ang integral ng lahat ng polynomials of degree less than or equal to 3, pero sasablay na siya sa isang polynomial of degree 4. Okay? So I hope that's clear. Mukhang medyo ginulo ko kayo or nilito ko kayo dun sa explanation, but I hope the definition makes sense to you. Okay? So, yeah, tingnan natin gaano ka precise yung trapezoidal rule. Okay? So, kailangan titingnan natin hanggang anong degree yung ng mga polynomials ang kayang i-integrate ng trapezoidal rule exactly. Okay? O yung approximate na nakukuha natin sa trapezoidal rule ay yung eksaktong integral ng mga polynomials na to. Okay? Now, an easy way to check it is to look at the error term. Ano nga ba yung error term sa trapezoidal rule? Remember that the error term in the trapezoidal rule is equal to this guy. Okay? Tas gusto nating tingnan ano yung mga polynomials na laging nagzi-zero yung error. Okay, so tanong natin, what are the polynomials for which this is 0? Okay. So, ibig sabihin, ano yung mga polynomials f na nagzi-zero yung error term? Okay? Madali siyang i-analyze by looking at this guy. Kailan ba nagzi-zero yung f double prime? Kasi pag nag-zero yung f double prime palagi sa sa class ng polynomials na to, sure tayo na degree of kasama siya dun sa degree of precision. Okay? So, look at this. F double prime of x will be 0 when? Kailan siya nagzi-zero? Para kanino mga polynomials? Of course, for constant polynomials and for linear polynomials, nagzi-zero rin yung second derivative. Pero kapag ka quadratic polynomial na, yung f double prime hindi na laging equal kay 0. So again, sure tayo kapag ka si f ay constant, ang f double prime ay 0. Pag si f double prime ay linear, laging nagzi-zero yung f double prime. Pero pag quadratic na si f, yung f double prime may not be equal to 0. So hindi na tayo sure kung nagzi-zero yung error sa mga quadratic polynomials. But we are sure that the error will be 0 for all constant and for all linear polynomials. So we say that the trapezoidal rule is of degree precision 1. Okay? So clear ba yun? Can I see some thumbs up kung clear naman yung definition? Sorry kung medyo ginulo ko kayo dun sa unang pasada ng definition. I'm still debating how to present it more clearly, but I hope the definition made sense. All right. Okay. Now, it seems that looking for the degree of precision of a particular numerical integration quadrature formula is daunting and quite cumbersome kasi kailangan nating isa-isahin. Kaya niya bang i-integrate eksakto lahat ng mga polynomial of degree 0? Lahat ba ng polynomial of degree 1? Lahat ng polynomial of degree 2? Tapos kailangan mo maghanap ng counterexample para malaman mo kung kailan ka titigil, right? Katulad dito, kailangan ko magbigay ng isang quadratic function kung saan kung saan hindi nagzi-zero yung error para ma-verify ko na degree of precision niya talaga ay 1 lamang. All right? And it is not that hard to find such a quadratic counterexample. Okay? Pero isipin nyo kung napakalaki nung degree of precision ng isang quadrature rule. Alam mo, degree of precision 8 siya. So kailangan ipakita mo na yung approximate galing sa quadrature rule ay eksakto para sa lahat ng constant, linear, quadratic, cubic, quartic, quintic, degree 6, degree 7 at degree 8 polynomial. Tas dapat mali na siya sa isang polynomial of degree 9. Okay? So ganun ka-tedious supposedly yung paghanap ng degree of precision. But thanks to the fact that if you remember, na-discuss yata natin sa Legendre polynomials na basis ng set of all polynomials of degree less than or equal to n, yung 1, x, x squared, x cubed, until x to the n. Tapos, ang kagandahan kung nag-math 120 na kayo or math 105, kapag ka meron kang basis, yung action ng isang linear operator dun sa basis elements will determine how the linear operator acts on all elements of the vector space. So, alam mo kung paano nag-act ang isang linear transformation sa kanyang mga basis elements, kaya mong i-characterize kung paano siya nag-work sa lahat ng elements ng vector space. So, pero dun sa mga hindi pa nag-120 or AMAT 105, it's fine. Papakita ko yung specific case para sa integrals. Kasi ang integrals or ang integration na isang linear operator. So kung gusto nating malaman kung ano ang degree of precision ng isang polynomial, 'di ba dapat eksakto niyang na-integrate lahat ng kung siya ay degree of precision n, dapat eksakto niyang na-integrate or eksakto niyang nakukuha yung integral ng lahat ng polynomials of degree n or less. Pero may isang polynomial of degree n plus 1 na hindi niya na eksaktong nabibigay yung integral. Alright? So if I want to check if my formula is of degree of precision n, okay, kailangan ko mag-consider ng isang generic polynomial of degree n. At gusto kong ipakita or i-force ang issue na ito ay pag in-evaluate ko yung integral na to, magko-coincide yun exactly dun sa ibibigay ng aking quadrature formula. Alright? Where here the a sub i's are all constants. Okay? Now, tingnan natin, ano ba yung integral ng p of x dx? So, papalitan ko lang si p nung mahabang polynomial definition niya. But thanks to the linearity of the integral operator, the integral can be distributed over the sums. And then all constant factors will come out of the integral, okay? And eventually we'll have this. Okay? Para pala masabi na nai-integrate na nakukuha ng quadrature formula natin yung integral ni p exactly, dapat pala, ang kailangan ko lang i-check ay nai-integrate ba niya ng eksakto yung dx? Nai-integrate niya ba eksakto yung x dx? Nai-integrate niya ba eksakto yung x squared dx hanggang dun sa nai-integrate ba niya ng eksakto yung x to the n dx? Because if that happens, again, if our quadrature formula can give us the exact values of the encircled integral in this long summation, then we are sure that we are getting the integral of p exactly. All right? So hindi ko pala kailangang isa-isahin lahat ng mga posibleng polynomials of degree n. Kailangan ko lang tingnan, yung quadrature formula ko ba, na-calculate niya ba eksakto yung integral ni dx, integral ni x, integral ni x squared, integral ni x to the n minus 1 hanggang integral ni x to the n. And if that happens, I'm sure that the quadrature rule will give me the integral of p exactly. Okay? Ito yung goal ng Gaussian quadrature formulas. Gusto nating makahanap ng appropriate weights and abscissas to achieve the highest possible degree of precision. And again, the cost of doing that is that we don't have any free hand in choosing the x sub i's. Unlike the Newton-Cotes formulas where we can use any arbitrary set of x's, sa Gaussian quadrature rules, kailangan piliin natin yung mga x sub i's precisely with their associated weights so that we can achieve the highest degree of precision. Tapos yun yung gagawin natin. And the derivation, as you will see in a moment, is actually based on solving a system of nonlinear equations. Okay? Now, so the process goes this way. First, you decide ilang points yung gusto mong gamitin. Okay? So say you have n points. Okay. If you decide to use n points or n abscissas, that will generate 2 times n unknowns. Kasi unknowns yung exabytes at unknowns din yung weights na i-associate natin sa bawat exabyte. So if you are thinking of using endpoints, hindi lang yung abscissas yung hinahanap mo. Hinahanap din natin ano yung mga weights associated with these abscissas, so that will give us a total of 2n unknowns. Okay? And then this 2n unknowns can be shown to be able to guarantee that the degree of precision is 2n minus 1. So this is the maximum degree of precision, 2n minus 1. Okay? So i-review natin. Kung gusto mong gumamit ng endpoints, kailangan bigyan mo ako ng 2n numbers. Yung unang n, sila yung mga x sa bias. Yung pangalawang n, sila yung mga w sa bias. Tapos, itong endpoints na to will give me a quadrature formula of degree of precision at most 2n minus 1. Okay? So, ibig sabihin, since this is still a quadrature formula, gusto nating mag-develop ng isang formula that looks like this, which will be true for all polynomials of degree 2n minus 1 or less. Okay? Pero again, nakita natin by the linearity of the integral operator, hindi ko na siya kailangang i-check sa lahat ng polynomials of degree 2n minus 1. Kailangan ko na lang i-check kung totoo ba tong statement na to. In other words, eksakto bang na-approximate ng quadrature rule yung given integral when the integrand are the following. Siya si 1, siya si x, hanggang siya kay x to the 2n minus 1. Yun lang yung kailangan nating i-impose. Dapat na-integrate or nakukuha niya yung eksaktong value ng integral ni 1, ni x hanggang kay x to the 2n minus 1 over the interval ab. And doing so will give rise to a system of nonlinear equations. Unfortunately, medyo limited tayo dito kasi pag malaki na yung value ni n, maraming equations yung involved at mahirap nang isolve yung nonlinear equation by hand. Pangalawa, hindi pa natin na-discuss or hindi covered sa Math 174 yung solution ng systems of nonlinear equations. Nasa Math 174, nasa Math 175 pa siya. So ngayon, mag-rely lang tayo halimbawa kay MATLAB o kay Wolfram Alpha or if you have Mathematica on your computers para isolve itong coefficients na to. If you're doing an exercise or doing it in the upcoming problem set, wag yung isolve ng mano-mano lalo na kung malaki yung n. Kasi mahirapan kayong isolve yun. So pwedeng gumamit kayo ng online solver or gumamit kayo ng MATLAB. Tapos sabihin nyo lang dun sa isasubmit nyo na PDF, computing the roots or the solutions of the following equations using MATLAB gives me the following. Okay? So hindi nyo kailangan gawin siya mano-mano. Take advantage of all the resources that you have. Okay? So let's illustrate now the process. I hope you have a good idea now how the process will go. But to make it a little bit more tangible, let's look at a specific example. So i-derive natin yung Gaussian quadrature formula that uses only one point. So n equals 1. Kung n equals 1, meron akong dalawang unknown. 2 times 1, right? Sila dapat yung abscissa na gagamitin ko. Yung abscissa na gagamitin ko. So siya si x1. At saka si W1. Ano yung weight na ibibigay ko dito sa function value na to, right? Para maging mukha siyang quadrature rule talaga. So meron akong dalawang unknowns. Isang point, dalawang unknown, tapos yung degree of precision ay 2n minus 1. So that would be 1. So ibig sabihin, kapag gagamit lang ako ng isang point, yung quadrature formula na madiderive ko, kaya niyang i-integrate eksakto lahat ng constant at saka linear polynomials. Pero wala nang guarantee na yung approximate na makukuha ko for all quadratic polynomials would be exact. Posibleng hindi na eksakto yung makuha kong value para sa integral ng isang quadratic formula. So again, that's going back to the definition of the degree of precision. Okay? Now, natutunan natin from the linearity of the integral operator na kailangan pala na para mag-guarantee na ma-integrate niya eksakto lahat ng constant at saka lahat ng linear polynomials, kailangan lamang ay ma-integrate or maibigay sa atin ng quadrature formula yung eksaktong value ng integral ni 1 at saka integral ni x to the 1. Okay? Right. So first is I want this equation to be true for f equals 1 and f equals x. All right? So if you substitute f of x equals 1, okay? Palitan nyo to ng f of x equals 1. So yung f ay magiging 1, integral lang ni dx. Ito 'yon. over the interval AB. Pag kinalculate nyo, ang sagot ay B minus A. Right? Tapos dito sa right-hand side, okay, dito naman tayo, plug in nyo yung f of x equals 1. So if f of x is equal to 1, then f of x1, no matter what x1 is, that will just be 1. So when f is equal to the constant function 1, then we'll have this. W1 is equal to B minus A. Yun yung unang equation dun sa system natin. Okay? Now again, the promise is that the quadrature rule that we will derive will be of degree of precision 1. So dapat kaya niya ring bibigay sa atin yung eksaktong value ng integral ni x to the 1. So palitan lang natin si f dito sa statement na to by the linear function x. So we'll have integral of x dx. So that will give us what? That will give us x squared over 2 evaluated from a to b. So that will be b squared minus a squared all over 2. And that's how we got this guy. All right? Tapos, dapat equal siya dun sa result ng quadrature formula. So dito sa quadrature formula, yung f of x ay papalitan ko ng x, right? So f of x is equal to x, plug in x1, so that will give us x1. So this will give us the right-hand side here, x1 times w1, okay? Which gives rise to the second equation in our system, b squared minus a squared over 2. Okay, so ito yung system of nonlinear equations na nakuha natin mula dun sa definition ng degree of precision ng quadrature formula. Okay? Now, it's for us to solve for the values of W1 and X sub 1. Luckily, the first equation spells out the value of W1 right away kasi si B at saka si A siya yung upper at saka lower limits ng integrals, so they are fine. That is just a constant. Okay? Tapos, so okay na yan. Alam na natin si W1. So ipa-plugin ko na lang yung value ni W1 na to dun sa pangalawang equation. I'll get B minus A over X. I'll have B minus A times X1 equals B squared minus A squared all over 2. And then solving for X1, we'll just divide both sides by B minus A. Tapos ito ay pwede kong i-factor na B minus A times B plus A. Ka-cancel ko yung B minus A. We'll be left with B plus A over 2. Or that's also A plus B over 2. Okay? So now we have found the two unknowns. Alam na natin dapat kung sino yung abscissa na pipiliin. It just so happened that that abscissa is the midpoint of the interval AB. And the associated weight is B minus A, or the length of the interval. And actually, this resulting quadrature rule is what we have seen before. This is the midpoint rule, one of the Newton-Cotes formulas. Okay? So ito yung pinaka-simpleng derivation kasi n equals 1 pa lamang. Do you guys have some questions about this? Bago tayo pumunta dun sa mas komplikadong example. I hope you get the process, okay? Okay lang ba?
Okay lang po, sir.
All right, thank you, David. Okay, so ngayon tingnan natin ano yung mangyari kapag halimbawa gustong gumamit ng dalawang points naman. And what would be the resulting Gaussian quadrature rule, okay? Now, to simplify things, okay? So gawin ko muna, i-normalize natin yung integration interval. So yung arbitrary interval AB, gawin nating interval -1 to 1. Okay? So we can do so by a change in variable. So we just let x be equal to b minus a over 2 times t plus a plus b over 2. Okay? So this will give us dx equal to what? This will just be equal to b minus a over 2 dt. So change of variable lamang para yung interval AB o yung upper and lower limits of the integral maging -1 to 1 lamang. because maganda siya para mag-zero yung mga integral ng yung ibang integrals ng powers ni x to the n. Okay? So if we do this change of variable, we'll get this. The integral from a to b of f of x dx will be equal to this guy. Okay? Now, we will use this fact. Tapos ang gagawin natin ay i-derive ko na lang pala ano yung mga abscissas na gagamitin ko if the integration interval is from -1 to 1. Okay? Tapos kung ano man yung abscissas na mako-compute ko using the similar method that we did before, sila yung magsiserve na t dito sa bagong integral na to. Or perhaps let's do this step by step. I-assume muna natin na yung yung interval of integration natin ay -1 to 1. I-derive natin ano yung abscissas at ano yung mga weights associated with them. Okay? And then if we will use this quadrature formula para sa isang integral ng integration interval ay other than -1 to 1, kailangan lang natin siyang i-rescale. Okay? So let's do the first thing first. Let's derive the Gaussian quadrature formula para sa interval -1 to 1 using 2 points. Okay? Okay, 2 points yung gusto natin gamitin. So dahil ang n ay 2, we will have 4 unknowns. Ang mga unknowns natin ay W1, W2, X1, and X2, right? The two abscissas and their associated weights. Sila yung kailangan nating i-compute. Okay? Now, we will assume that the integration interval for a moment is the interval -1 to 1. Okay? So sabi natin, dapat okay, meron akong 2 points, so meron akong 4 na knowns. Yung degree of precision ay magiging 2 times 2 minus 1 equal kay 3. So ibig sabihin, dapat kayang ibigay sa atin ng quadrature rule yung eksaktong integral ni 1, ni x squared, at saka ni x cubed over the interval -1 to 1. Okay? So yun yung gusto natin mangyari. Ang itsura ng quadrature rule natin ay ito. Okay? Sum ng W1 times f of x1 plus W2 times f of x2. Ito yung itsura ng quadrature rule. And we want this to be exactly equal to the integral of f of x dx from -1 to 1, where f is 1, x, x squared, and x cubed. All right? So let's see what will happen. Okay. Now, if we will replace f by 1, okay, so integral lang from -1 to 1 ni 1 dx, so that will just be 1 minus -1, so that would be equal to 2. That's the right-hand side. Tapos, galing dun sa quadrature rule, pag pinalitan ko si f ng constant function 1, this guy will just be 1, this guy will just be 1, so we'll have w1 plus w2. And that will give us the first equation in the system. Okay? Now, the second thing to do is to plug in f of x equals x. All right? So, punta ka uli dun sa integral, -1 to 1 ng x dx. So, this will give us x squared over 2, evaluated from -1 to 1. That will give us 0. And actually, this will be true for all odd-powered integrand. Kapag ka meron kang x to the k where k is odd, laging nagzi-zero lamang yung integral. Kaya maganda na nandun tayo sa interval -1 to 1 kasi symmetric siya. Okay? So lahat ng odd functions nagzi-zero yung integral niya over a symmetric interval. Okay? Now we will replace to get the left-hand side, puntahan natin yung quadrature rule. Okay? Lahat ng f dito papalitan ko ng x. So ito ay magiging x evaluated at x1. So we'll have w1 x1. And then this guy will be x2. So that's how we got that. Okay. Pero yung ating hinahanap na Gaussian quadrature rule ay dapat of degree of precision 3. So dapat kaya niya ring integrate eksakto yung yung polynomial x squared. Yung integral ng x squared from -1 to 1 ay equal kay 2/3 Tapos babalik na naman ako dito sa quadrature formula. Lahat ng f, papalitan ko ng x squared. So the first term will be w1 times x squared evaluated at x1. So that's going to be x1 squared plus the weight on the second function value times x squared evaluated at x2. So we'll have that. Kaya meron tayo nito. Nawala yung subscript dito. All right. And then the same thing goes for x cubed. So if you replace f by x cubed, we'll get this third equation. And now we'll have a system of, actually here, what do we have? We have 4 unknowns and we have 4 nonlinear equations. Okay? So ito yung, yan yung mga equations na dapat natin isolve. Pero again, by hand, mahirap na siyang isolve kasi nonlinear na nga siya tapos 4 by 4 pa. So let's try to do it via MATLAB. Typically, I use Wolfram Alpha or Mathematica para isolve siya. Pero dahil MATLAB yung may free access tayo, gawin natin siya sa MATLAB. So pakitandaan yung equation, you might want to take a screenshot of it or copyhin siya. Or pwede pala ako na lang. So lipat ako ng screen. Pakita ko yung MATLAB screen ko. Where is MATLAB? Okay, there you go. Okay, so I hope you guys can see my MATLAB screen. Pakisabihan na lang kung maliit yung font. Okay, so ano ba yung sinusolve natin? Sinusolve natin si x1, x2, w1, and w2. I will declare them as symbolic variables. Okay, so x1, x2, w1, and w2. This will just prompt MATLAB to think of x1, x2, w1, and w2 to be symbolic variables. Hindi niya to hanapan ng constant values. Okay? Now, paano natin ipapasolve kay MATLAB yung system of equation? Well, you just, okay. Umpisa natin dito. Container for the solution. So, ibibigay sa atin ni MATLAB, papasolve natin yung value ni x1, x2, w1, and w2. They should be enclosed in brackets kasi para matreat siya ni MATLAB as a single vector. Okay, remember vector-based si MATLAB. So, ilagay nyo sa loob ng isang vector lahat ng variables na pinapasolve nyo kay MATLAB. Okay? Tapos, paano natin sasabihan si MATLAB na isolve ito? Lagyan ng equals. Okay? Para i-assign niya itong vector na to consisting of x1, x2, w1, and w2 to be the result of the following calculations na nandun sa kanan ng equal sign. Now, ano yung function para mag-solve ng nonlinear system? Simple lang, solve. Okay? Tapos, it will take some inputs. Okay? Ano yung mga inputs? Meron dalawang inputs dito. Okay, I'll put them inside brackets. The first brackets will be reserved for the equations that you want to solve. Ano yung mga equations dun sa system, okay? So let me just see what is the system again. So ito yung system natin. Unang equation natin ay W1 plus W2 equals 2. So kapag nagpapasolve kayo ng equation kay MATLAB, yung equal sign dun sa equation should be double equal sign. Kasi kay MATLAB, yung isang equal sign lamang ay value assignment. So ibig sabihin, yung value sa kanan, yung ite-take niyang value sa kaliwa. Pero sa equations, sineset natin yung value, right? Hindi natin alam yung value ni W1 and W2. We just know that W1 plus W2 must be equal to 2. So kaya double equal sign yung gamit dyan. And then the equations in the system must be separated by commas, okay? So, yung pangalawang equation dun sa system ay W1 times X1 plus W2 times X2. And it should be equal to 0. All right, yun yung nakita natin kanina. Third equation will be W1 times X1 squared plus W2 times X2 squared. And that should be equal to 2/3. Okay. And then the last equation is W1 times x1 cubed plus w2 times x2 cubed equals 0. Okay. So ito yung apat na equations na na-derive natin mula dun sa definition ng degree of precision. Okay? And they will be the first vector input to the solve command. The second input would be the variables na gusto nating ipasolve. Just make sure na gagamitin natin yung same order nung nandun sa kaliwa ng equation para isosolve niya at i-assign niyo yung values in the correct order. So i-copy ko na lang to. Okay. Ibig sabihin yung unang output ni solve ay dapat si x1. Yung pangalawang output ni solve ay si x2. Pangatlo ay si w1. Pang-apat na output niya ay si w2. Para yun din yung corresponding ordering ng pag-assign natin ng values dito. Okay? So kaya dapat crucial yon. Yung order dito dapat kaparehas ng order dito sa loob. Okay? Because x1 will be assigned to x1, x2 will be assigned to x2, w1 will be assigned to w1, and so on. Because here you could have chosen a different set of variables. Probably you could have said this is A, B, tapos ito gawin mong C, tapos ito ay D, okay? Tapos ang i-assign ni Solve o ni MATLAB dun sa value ni A ay yung unang variable na pinapasolve mo sa kanya. So gagawin niya yung value ni x1 na manggagaling dun sa solve command, siya yung tatawagin ni MATLAB na A. Yung value mula sa solve command na compute niya for x2, siya yung i-assign niya para kay B. Okay? Pero to keep it uniform, gamitin ko na yung same variables para sa kanila. Because anyway, hindi ko na naman gagamitin yung x1, x2, w1, and w2 later. Right? And then, okay, you can run this. You can press F5 or the run button here on the taskbar. We'll get this. Okay. Nakikita niyo sa command window yung output. So, kay x1, meron siyang dalawang possible values. It is a square root of 3 over 3 or negative square root of 3 over 3. Yun yung dalawang posibleng values ni x1. Hindi pala unique yung solution, okay? Now, kay x2, meron din siyang dalawang values. So, ibig sabihin kay x1, kung ito si x1, dapat si x2 natin ay ito. So, if x is positive root 3 over 3, dapat si x2 ay negative root 3 over 3. Okay? And so on. So, pwede niyong isipin yung first components, sila yung magko-comprise ng unang dalawang values ni x1 at ni x2. Tapos ang weight para sa kanila, ang weight para dun sa una ay 1, ang weight para sa pangalawa ay 2. Okay? Now, if you use the other solution, actually symmetric lang naman yan. Sinabi niya lang na si x1 posibleng negative root 3 over 3. Tapos yung kapartner niya ni x2 dapat si root 3 over 3. So parang katulad din siya nung kanina, nabaliktad lang yung order. Kasi symmetric yung equation natin eh. Tapos kung yung second components yung gagamitin mo, yung weight dapat para sa first term ay 1, weight para sa second term ay 1 din. Okay? Actually, I think there's a better way on how to display this. You can type pretty. Okay? Tapos ilagay mo yung vector na gusto mong ipa-output sa kanya in a prettier way. Copy ko to. And then I'll hit F5 for run. Okay. So ito yung makukuha kong solution. So the first solution is this guy. Ito si X1. Oops, ito si X1. Ito si X2. Ito yung weight para kay X1. Ito yung weight para kay X2. Then ito yung other solution, other quadruple solution. This would be your X1. Ang weight niya ay 1. Ito yung X2 mo. Ang weight natin ay 1 din. So these two solutions coincide with each other. So you can just pick this one out to be your actual solution. Okay. So you see how simple the MATLAB solver for this 4x4 system is. So pwede nyo itong gamitin if you'll be doing 5x5, 6x6. Pero limited to. Pag masyado na malaki yung system, mahirapan na siyang i-computein yung solution symbolically. Okay? Kasi yung symbolic calculations, napaka-expensive niya pag pinagawa sa ating computers. Okay? So is the code clear, guys? Kasi lilipat na ako in probably 30 seconds pabalik dun sa vortex. So you can screenshot it. Ba ba itong yan? Hindi kasya yung buong equation. Okay. So, but I hope you get the idea nung syntax. So if you want to screenshot it now. I'll give you 5 seconds para i-drag ko naman siya para yung kalahati ng screen makita niyo naman. Okay? So ito yung kalahati. Ito yung kasunod. Ipagtikitin nyo na lang yung screenshots nyo. Okay? So let's see. So let me go back to the notes. Okay. So I hope you guys now see my PDF file. Okay. So yun din yung nakuha niya dito. Ang ginamit ko pala yung pangalawang solution. X1 was taken to be negative square root of 1/3, or that's the same as square root of 3/3, right? And this would be my x2. And then yung quadrature formula natin of degree of precision 3 would be this guy. Okay. But take note that since the nodes or the abscissas that we chose are over the interval -1 to 1, so nag-work lang siya para sa mga integral na ang integration interval ay from -1 to 1 lamang. Okay. I'll notice that the weights here are 1 and 1. Okay. Tapos ito yung x sub 1, ito yung x sub 2, ito yung w1, ito yung w sub 2. Okay. And now let's illustrate how this is used pagka yung integration interval ay hindi -1 to 1. Kailangan natin siyang i-translate ng kaunti. Okay? Now you can think of the x1 and x2 here that we have computed to be the t-values in the translation formula that we obtained by the change of variable kanina. Okay? So tingnan natin to. Example 9.2. Again, we want to approximate ln2 using the 2-point Gaussian quadrature formula. So, continuation to nung examples mula sa Newton codes, kaya ln2 uli yung ginamit ko. So, we know that ln2 is equal to the integral of 1 over x dx from 1 to 2. Okay? Tapos, from our derivation above, yung 2-point Gaussian quadrature rule ay equal dito. It's of degree of precision 3. Okay? Tapos, from the change of variable that we have seen earlier, ito yung itsura ng translation kapag ka yung integration interval ay hindi na -1 to 1. All right. So that means our f here is 1 over x dx. Tapos yung t-values natin ay plus or minus root ng 1/3. Okay? So ibig sabihin, instead of using just -1 over root 3 here, papalitan ko siya nung translation formula na nandito. Okay? So still the weight is 1 and 1 para sa kanila. So meron tayong 1 times 1 na weight doon. Nakalimutan ko pala yung b minus a over 2 dun sa harap ng integral. Copying ko siya doon. Okay? So doon nanggaling yung 1/2 sa labas. Tapos ngayon, para sa ano yung value natin para sa integral na to? Integral from -1 to 1. Na-derive na natin yung quadrature formula para dun sa integral from -1 to 1. Ang weight niya ay 1. Ang weight niya ay 1. Pero yung function values na na-compute natin ay t-values. Negative root of 1/3 and positive root of 1/3. Pero yon ay nag-work kapag ang integration interval ay -1 to 1 lamang. Dahil ang integration interval na natin ngayon ay from 1 to 2. So ibig sabihin dito, papalitan ko yung t ng root of 1/3 or negative root of 1/3. So kaya ako makukuha ito. Tapos ito naman, papalitan ko siya nung x2 na na-compute natin mula dun sa Gaussian quadrature. So yung node na gagamitin natin, yung abscissa na gagamitin natin ay root of 1/3. Pero dahil translated yung interval, yung 1/3, titingnan ko siya as the t-value, ipa-plug in ko siya dito. Okay? So we'll have the function value of this guy, which is the translation of root of 1/3 papunta sa interval 1 to 2. Okay? Ito rin yung same translation formula na ginamit natin dun sa Chebyshev nodes saka sa Legendre nodes, yung pagta-translate sa kanila. So yun din yun. And then plug this in into 1 over x, plug this in into 1 over x, perform the calculations, and you get this guy. And this is pretty close to the actual value of ln2. Actually, you will have just 0.12% relative error. So maganda pa rin yung approximate na nakuha natin using the 2-point Gaussian formula. Okay? Now, yeah, I think that's it. So ang crucial things dito ay dapat marunong kayo mag-setup ng system of nonlinear equations para makuha natin yung unknown abscissas and the unknown weights for each of the abscissas, at least on the interval -1 to 1. Second, make sure to know how to compute the solutions to that nonlinear system, at least with the aid of MATLAB or any online solver that you can find na mas familiar kayo. And then pangatlo, wag kakalimutan kung yung integration interval nyo ay AB, ay hindi equal sa -1 to 1, kailangan yung gawin yung translation process. Okay? Now, we'll look at some more examples on Thursday. Pero do you guys have some questions for now? Tingnan ko kung ano yung coverage. Maiksi na pala yung susunod kasi ibibigay ko lang yung table of the first few Gaussian weights and Gaussian abscissas and weights. Pero I'll talk more about that next time. And I will illustrate further yung pagta-translate kasi isa pa lang yung examples natin ng pagta-translate. Try this one out, try to figure it out. Let's look at another example on Thursday, but let me know if you have some problems with example 9.2. And then I'll give some hints for exercise 5.2 on Thursday. Okay? So do you guys have questions? Masyadong tahimik. Parang wala akong nakitang kahit reaction kanya, kahit mga thumbs up. Okay lang ba? Or meron bang part na nakakalito?
Okay naman po, sir.
Okay naman po.
Hindi naman po, sir.
Okay, finally, I heard your voices. Okay, so yeah, I think that's it for now. Hopefully, clear siya at kayang-kaya yung susunod na exercise. So that's it for today, guys. Thank you all for coming. Enjoy the rest of your day, and let's see each other again on Thursday. Bye, everyone.
Thank you po, sir.
Thank you po, sir.
Thank you, sir.
Okay, you're welcome.